Wordsmith Wizards, I'm Professor John Gallagher, and in this CircuitPython school lesson, we're going to learn how to get text on our displays. We'll talk fonts, positioning, and I'll show you how the text output works across displays, demonstrating this first on a 320 by 240 TFT display, and then I'll show you how we can apply what we learned with just a little modification to get the goodness to show on a 64 by 32 LED matrix. So, let's talk text. If you're new here, welcome. You might want to check out the playlists to see how we got here. So you'll be able to perform most of what we do with just about any CircuitPython compatible display. But in this lesson, I'm going to work with a 2.2-inch ILI 9341 TFT display, at least initially. This is one that my students use in our semester-long course, and we learned about this in a prior lesson. And I'm going to be using a Raspberry Pi Pico 2W, one of the boards we use in class. Now you should be able to use all of the text drawing concepts I'm about to demonstrate on most CircuitPython boards and displays if you've got things wired up and configured properly. Now I've got a GitHub repo for you. This includes fonts that we're going to use in this lesson, and you can find the GitHub repo at this URL, and this URL is also in the video description. So open a browser, head to that location, then click on the green code button in the upper right hand corner, download as zip, find that downloaded repo on your computer, unzip if you need to, open up that folder, and then drag the fonts folder into your CircuitPy volume. So it's important to note, with this code I'm assuming that you've got a fonts folder, lowercase fonts, on your CircuitPy board, and it contains the fonts that I'm showing here. Then I'll launch PyCharm. In an earlier lesson I demonstrated the configuration code to set up the ILI 9341 display that I'm using. That's this $5 board that I bought off of AliExpress. I have the setup code in our CircuitPython tip sheet, so I'm going to go there now. The tip sheet is very familiar to our students, but if you don't know about that, well, the URL is also in the description. Here it is. Then I'm going to search for displays, and I'm going to find the ILI 9341's code, copy it, paste it into PyCharm, open the terminal, get into TO, save, and when I look over at my display, I see some text, but the font is super tiny and not at all impressive. Well, in an earlier lesson, we mentioned very briefly, with most standard TFT or OLED displays, CircuitPython will output whatever shows up in the console to the screen. So if you have print statements or error messages, you're going to see that on your display once things are configured. Now you won't see that on LED matrices, but most of the other stuff we'll learn in this lesson will apply to those as well. Now this mirroring of the console on the display goes away as soon as we start working with DisplayIO. Now DisplayIO is the primary library that allows your CircuitPython board to talk to its display, and it's got several components. First, you're going to configure a display, and you usually do that with a special library that's appropriate for the display, like the ILI 9341 library. But when you set up your display, we're typically going to call it display. That's the variable name we're going to use for the object representing the display. And most of our code standard across displays will work against this object. And that's even if they're different displays that have been configured using different libraries. That's part of the magic of CircuitPython. Now there's also something called a group. Now a group is a rectangular space. Think of it as a canvas where you can draw things like labels for text and tile grids for graphical elements like shapes and images. And the main group is called the root underscore group, and it's the same size as the display. Now while it's possible to create other groups and add them to the root group, for now we're going to be adding our labels directly to the root group. And we'll use that using the append command. And again, anything we append to the root group will show up on our display. Now in DisplayIO, the label's a container that holds text, your string that you want to display on screen. So what we'll do is we'll create a label and we'll add it to our root underscore group. Now a label can contain the label's font. The terminalio font is built into CircuitPython, but we've also loaded a folder named fonts that contain other fonts in the BDF format. The label also has the text, which is a string that makes up our content, and initially we'll use a position, think XY coordinate, for placing the label in our group. We'll also give our text a color, and there are a bunch of other optional label properties too, like the scale, which is a factor we could use to resize the label. And one other thing that's really important to know, when we plot elements on a display, the coordinate system used in CircuitPython, and really in most computing, is different from what you learned in geometry. So in geometry, the origin point is in the lower left-hand corner for Cartesian systems. But on computers, the origin point 00 is almost always in the upper left, with positive X going right and positive Y moving down. Now the TFT screen that I'm using has dimensions of 320 by 240, and the LED matrix that I'll show later is physically larger but has fewer dots. It's only 64 by 32. And also, if you try to show any values that are off screen, say you try to plot things with negative values or values that are beyond the maximum X and Y, they're still computed and your code will still run, but they won't show up unless you change the coordinates so they'll show on screen. Now, let's display some text. We always start working with DisplayIO with these two steps. We'll reset DisplayIO so that the displays don't contain any lingering changes from earlier runs, and I already have that in our configuration code up here. Before we do anything, see DisplayIO.release_displays, open and close parens. And pro tip, sometimes when you're working on displays, if you find that your code doesn't seem to be working the way it should, sometimes your display needs a hard reset, and you can do that by unplugging and replugging in your board. Then we'll create a display, and this code varies depending on the type of display you're using, the microcontroller board you're using, and how you've wired your display to your board. So this is the code using the ILI 9341 display, wired to a Raspberry Pi Pico in the way demonstrated in my prior lesson. Now I no longer want to print this text in the tiny font at the bottom of the screen, so let's delete this print statement. And now we mentioned, in order to put text on our screen, we're going to be using the label class. The configuration code that I pasted in already has the import statements I need. Now it is worth noting, especially if you look at any other code online, there are a few ways to create a label, and we're going to be using the bitmap_label library. Now there's also a label library that has a label class. This is an older library. Always use the bitmap_label library for label if you can. It's newer, it's more memory efficient, and it includes more features. Now before we create a label, let's first create a group, and our first group is going to be known as the root_group, which acts like a canvas to hold everything on our display. It's got the same dimensions as the display, and we create the group like this. We'll call it group and set this equal to DisplayIO.G group, open and close parens. So this creates the empty group, and we'll assign that group to our display with display.root_group, and that equals group. So now let's create our first label. We'll give the label object a name. I'm going to call this top_label. This is just a variable name, but we'll set this equal to the label class with a capital L, and we'll open parens to send this to the label factory, and I'm going to press return after that open parens. PyCharm adds the closing paren and indents me, and I'm going to write my parameters on separate lines with commas after them just because this will make things easier to read. Now our first parameter is going to be the font. The order doesn't matter as long as we've got the parameter labels in there, so we'll put in font, and this is going to be equal to the built-in font, which is terminalio.font, F-O-N-T, all in caps, comma at the end of each of these parameters. This isn't a pretty font, but we're going to replace this with a custom font in just a bit. And then we're going to add the text, and this is going to be equal to, in double quotes, up top, exclamation point, comma after that. And one thing that we need to do with the bitmap_labels label class, at least currently, although this might be a bug and fixed in future versions, is at least right now we need to set the background_type parameter equal to true. Remember in Python that's with a capital T. Currently without this, the text might have too much additional padding around it and it might align awkwardly. Make sure you add a comma after each parameter. Then we'll give the label a position, and we're going to start by using XY coordinates, although I'll show you how to use anchoring techniques in just a bit. So let's see what happens when we pass in the origin. Remember that 0, 0 as our X and Y position, so on separate lines we'll say X equals 0, comma, Y equals 0, comma, and then on the next line we'll add a color with color equals, and in parens, why don't we make it green? So I'll say 0, comma, 255, comma, 0. You'll also see lots of people use hexadecimal colors. The hex for green is 0, lowercase x, 00, FF00. Those are just base 16 numbers, and FF is the equivalent of 255. Then to display this text, we add it to our group. So after the closing paren in label, we'll say group. Remember, that's our root_group. That's the size of the display. And we'll say .append in parentheses, passing in top_label. We make sure that we have while true, pass underneath that. And just above the while true, why don't we put in a print statement just so that we can see something print out to the console. We'll say print running text label demo, and why don't we change the first comment in our code. So this is going to be the name of what I'll save this to in CircuitPython school. The file will be called text-label-demo-, and I'll put in the name of my display, ILI9341.py. You can change the display name if you're using a different display type. Then we'll open the terminal, we're in TO, we'll save the code, and it runs, but if we take a look at our text, we can see it's cut off vertically about halfway down through the letters. Not at all what we expected. Now the reason for this is that the Y position is plotted relative to a baseline, which runs through the center of the label's bounding box. Now the bounding box is the rectangle that encloses the label, it encloses all of our text. So normally when we talk about a font's baseline, that's usually the line where the bottom of most of the letters touch and where parts of some letters extend below, like the tail of lowercase letters like P, Q, and Y. Those would extend below a baseline, but in practice, in CircuitPython, the baseline is more like the center of a font's height, and since the baseline of the label determines where the coordinates are plotted, the label starts here, at the vertical middle of our bounding box. Half of it is below the baseline, it's visible, the other half is above the visible coordinates in the display, it's not seen. Now one way we can fix this is by shift the plotting down by half of the height of the font, or half the height of the bounding box. Instead of calculating the precise size of the bounding box, I'm just going to use the value 14, so I'm going to change my y equals 0 to y equals 14. Save, and cool. We see this, but as we'd say in Boston, it's wicked small and not a good user experience. Let's use a different font. Now, to use custom fonts in CircuitPython, you need to first import the bitmap_font class from the adafruit bitmap font library. So we do that with this line from adafruit_bitmap_font, import bitmap_font. Then we'll create a font object that will get our font file from our CircuitPy board. And I usually do this further down in our code, just below where we set up our root group. So below display.root_group equals group, I'm going to give the font a name. I'm going to call this label_font, and I'm going to set it equal to bitmap_font dot, and we're going to use the load_font method. And in between parentheses, we pass in a string that equals the path of the font plus its font's name. So since we stored our font in a folder on our CircuitPy volume called fonts, we'll say /fonts/, and then the name of the font that I want to use is HELV, all lowercase, plus capital B 18.bdf. Now, to use our font in our label, all we need to do is to replace whatever we had in our font parameter where we created the label object using the label class. So I'm going to replace terminalio with the variable of the font object we just created, which is label_font. And since this font is labeled 18, I'll assume that that means it's 18 points tall, although you really can't rely on that. But to try to fit things in, I'm going to change y equals 14 to y equals 18, then save, and look at that. Much easier to read. Now, if you want this even bigger, one of the things we can do is we can add a scale parameter to our label class. Now, scale allows us to increase a font's size by a multiple, but scaling also introduces jagged edges, because it's sort of like dragging a bitmap picture into a larger space. The font isn't designed for that larger space, and the reason for this is that the BDF type fonts that we're using aren't like the fonts that you use in Mac and Windows. Those fonts are drawn with math, and they're re-rendered with each size change, so they're smoothed out regardless of their size. Now, the BDF fonts have each character drawn at a specific size using individual dots, individual pixels. And if you want a different size font, you need to install another file with each character in the font drawn with specific pixels at a different size. But just to see this in action, we can add the scale equals, how about 3 as a parameter, comma, save this, and whoa, much bigger. Now you can also see the jagginess that I warned you about in the curve of the font, but you can also see that since we placed our font at y equals 18, that doesn't allow enough space up top to show the whole font on screen. Why don't we change y equals 18 to y equals 24, save again, and there, now we can see the whole font on screen. But let's go back and remove this scale line from our code. I'll also change y back to 18. We'll see if this holds up. Now, because of the jagged edges that show up when you use scale, it's probably a better idea to use bigger fonts if you've got them. The larger fonts are designed to render on screen more clearly without the jagged edges, and if you look at that fonts folder in our CircuitPy volume, we dragged over a bunch of different fonts here. There's one called HELVB24. So I'll replace the 18 with a 24, save this, and look at the results. And this is bigger than our prior font, looking good. We've also got one called Collegiate-50, and C in Collegiate is capitalized. Let's try that one. Save, and it'll run. I should probably have had TO open to see if I got any errors if I spelled a font wrong, but things are looking good. And it's not exactly 50 points tall, but it's definitely bigger. Cool. We've got another one in here called Rounded Heavy, which is all one word with a capital H-46. Let's try that one. Save. And hey, look at that. It's tall. It's all caps. Cool. And just to show you, if we wanted a tiny one, well, we could scale things down to HELV capital B08. Save. And oh, that's most pequeño. So let's head back to HEL capital B18. This is a nice font size. Now, a few other things to know. There are 2 different types of fonts that we can use in CircuitPython. BDF fonts, which we're using right now, and there are also PCF fonts. Those are actually more compact versions of BDF fonts, but there's another way that we can use Circup to find and install fonts that are as small as PCFs, and they'll be installed like CircuitPython libraries. Now, there's a bit of complexity to that, and we're going to use Circup for it, so I'm going to postpone that until a future lesson, but keep at that playlist because you'll soon see a lesson on how to access a huge array of fonts in lots of different sizes. Oh yeah, and before we move on, why don't we save this to our CircuitPython school folder using the name text label demo. I'll give it the name of my screen, ili9341.py, and always make sure that you close that outermost tab so we're back at code.py. So up until now, we've been placing things using X, Y coordinates on our group. But there's a better way to position text on screen. Instead of using X, Y coordinates and guessing where we want to place an object, we can use an anchoring technique which involves setting an anchor point and an anchor position, and both of these can be swapped out for the X, Y position parameters in a label. Now the anchor point is like a point where the label is pinned, and everything else drawn in the object flows out from that point. And the anchor position is the XY coordinates where we want to place the label on screen. Let me give you some examples to show you how these things work together. Here, imagine this is a blank screen. Actually, there are two blank screens because I want to show you lots of examples. And if we calculate the anchored position as at an X value of display.width, that's 320 in my example, divided by 2, and Y at display.height, that's 240 in my example, divided by 2, then we'll go right in the middle of the screen. And remember, when we perform division with double slashes like this is called floor division, which is like dividing a value and throwing away any remainder. This is a good way to make sure that when we divide by integers, the result is also an integer, and we want to do that here because we don't want any fractional coordinate points. No decimals in our coordinate values. Now again, this thing called an anchor point defines which part of the object's bounding box is its anchor. So think of it as the point where the object is pinned and everything else drawn as part of that object flows out from that point. Now anchor points aren't expressed in XY values, they're expressed as fractions of the bounding box. For a label, that's the box that encloses our text. So 0 is no movement on that axis, and 1 is complete movement to the other end, 100%. So consider this. If we have an anchored position in the center, display width divided by 2 and display height divided by 2, we're going to draw a label from this position right in the center. But if we also give the anchor point for our bounding box as 0, 0, we say we should draw the label from 0 movement from the origin X position, that's in the far left, and 0 movement from the Y origin position, which is at the top of the label. So 0, 0 is the upper left corner of our label. We pin that at our anchored position, which is right at the center. Everything draws out from here, from top left to bottom right. Cool. So what if we have 0, 1 as our anchor point? Well, that means that the X value doesn't move 0, so we stay at the left, but the Y value moves 100% the full distance 1 to the bottom of the label's bounding box. So we draw like this, with the bottom left pinned. See the difference? 0, 0 flows down to the right, but 0, 1 flows up and to the right. Now we mentioned the anchor point values are fractions of sizes of the bounding box. So what if we say the anchor point is X 0.5 and Y 0.5? Well, that means pin at 50% of the X and 50% of the Y and flow out in all directions from the center. That's the center of the label. Remember, anchor point applies to the label or the object that we're positioning. That's what we've got here, right in the middle. Very cool. Now, if we had 1, 0 as our anchor point, where do you think that pin would flow from? Well, if X value is 1, that means 100% movement from the left to the right, the full distance of our bounding box, and Y has 0 movement, so we remain at the top, so our anchor point is in the upper right and everything flows to the lower left. And finally, an anchor point of 1, 1 means 100% over from the X, so we're at the far right, and 100% over from the Y, we're at the far bottom. That means we're anchored in the lower right, and everything flows to the upper left like this. So the anchor point is a fraction of the size of the bounding box, that's the box our label is in, and the anchored position is, at least right now in the way that we're using it, the dimensions in real XY coordinates, not fractions, of our display. Now, even though we're talking about labels here, we can also use this concept with tile grids, which hold images. We'll talk about that in another lesson. Right now, we only have one group, which is the entire display area, but it is possible to create groups of different sizes, and if you did, the anchor position would plot within the coordinates of that group. So let's try this out by replacing our existing label with a bottom underscore right label like this. The label's name is bottom right, and why don't we add the text as a bottom right, capital B, capital R. Then let's delete the X and Y coordinates, and instead we'll add anchor underscore point, setting this equal to, between parentheses, 1, 1, and that's going to anchor the label's bounding box to the lower right. Now, where should we position that on our display? That's what the anchored position is all about, and we're going to set this equal to, in between parentheses, display.width, display.height, add a comma at the end, and since my display is 320 by 240, that's going to move us to 320 by 240. We'll set this to green, 02550. Make sure we do a group.append with our bottom right label name. We change that. This time I'll open up the terminal and make sure we're in TIO so we can see if we have any errors, and save this. No errors. Whoa, that's positioned perfectly in the lower right. Nice. And now that I've showed you how to do this, it's time for a challenge. This is the 4 other positions challenge. I want you to create 4 other labels: top underscore right, top underscore left, middle, and bottom underscore left. Set each label's string to its label name with a space, and capitalize each word with no underscore. You can see it on the screen on the right. Place each label in its respective corner with anchoring at a given point. For example, top right should be anchored at the position that's at the top right of the screen. The middle label should be right in the middle of the screen with its anchor point set to the middle of the label, the absolute middle. And why don't you mix up the colors as shown? So top left should be blue, top right should be red, middle should be white, and bottom left should be yellow. That's 255, 150, 0. We'll save this as labels anchored to 4 corners and middle.py. And one thing we'll notice is that the bottom left isn't perfectly aligned with the bottom right. That's because the characters at the bottom left don't have any descenders. You see how the G and right hangs down below what should be called the baseline, but we don't have that on the left-hand side. These guys are uneven. If you can figure out how to fix that, bonus points to you, but I'll also show you how to do it. So why don't you pause, give this a shot. I know you can do it. And when you're done, resume, and let's compare answers. So let me close the terminal and set the top comment to labels anchored to 4 corners and middle. And my label code is going to be the same with just a bit of changes. So I'm going to highlight my whole bottom right code and copy it, paste it above bottom right. I'm going to give this new label a name, top underscore left. I'm going to copy that. I'm going to paste it down inside of the group.append. That's very important. You want to make sure that you add your new label to the group. If you don't do that, your label will never show. Then I'm going to change the text to say top left. And we want to change our anchor point. Remember, this is in a fraction, 0 to 1, and this is the anchor point from which we draw our entire bounding box for the label itself. And since we want that to be in the top left, well, that's going to be 0, 0. Don't move it all on the left. Don't move it all down. I'll change my comment to say top left, but we also need to give this an anchored position. This is where we're going to anchor our label from its anchored point inside of our group, which for us is the size of our display, and that's going to be in display point 0, 0. I'll get rid of the comment on this line and the comment in our color, and to set this to blue, it should be 0, 0, 255. Then I'm going to highlight this whole label, copy it, paste it below. This next label should be called top underscore right. I'm going to copy this and paste it in between the parens for group.append. That'll draw this label. I want to make sure the text says top right. The bounding box anchor point for the top right is going to be fully over to the right. That's 1, 0. We're not going to move it all down. That puts the bounding box at the top right, and then where should we anchor the position in the screen itself? Well, that should be at display.width, 0. That'll put us in the upper right-hand corner. Then I'll copy that last label, paste it down below, change the name of this label to middle, copy that, and paste it in between the group.append parens. Change the text to middle, and to get right in the middle of our bounding box, well, our fractional anchor point is going to be 0.5, 0.5, 50% over on the x-axis, 50% down on the y-axis. Remember, that's going to anchor the middle of the bounding box of the label, but where should we position that anchor point in the overall display? Well, that's what the anchored position is all about, and that should be display.width /2, display.height /2. And I'll put in a comment that says / is floor division, which will return a value without decimals. I want my color to be white here, which is 255, 255, 255. And we need one more label, so I'm going to copy my middle label and paste it just below. Change the label name to bottom underscore left. Copy that and paste that in between the appends parens. The text will be bottom left. The anchor point will be 0, 1. Don't move left, but move all the way down to the bottom. And our anchored position should be 0, display.height. Change this color to yellow. That'll be 255, 150, 0. And why don't we change our print string to read 4 corners and middle demo. And there's one change I forgot to make. The top right corner is supposed to be the color red. I forgot to change that, so let's set that to 255, 0, 0. Then open the terminal, save, and this is looking good, just like I asked you in the challenge. But I said notice that we have a misalignment between the lower left corner and the lower right-hand corner. That's because the tight bounding box in the lower left does not have any descenders, where in the lower right we have the lowercase g, which is a descender. That boosts the bounding box height up. Now, there are a lot of ways that we can fix this, and there are some ways we can perform some math to calculate this, but frankly, in most cases, it's overkill. Most of the time, you'll have labels that are going to be more or less constant. So you can just nudge your point values up or down as needed, and that's exactly what I'm going to do right now. I'm going to head in the bottom left anchor position, and what I want to do is shift my anchored position up. So I'm just going to subtract 6 points from display.height. I'm guessing that lowercase g descender is about 6 points. Then I'll save this and take a look, and hey, that looks pretty aligned to me. Nice work, you display dynamo. Why don't we save this file to our CircuitPython school folder? Always close that outermost tab. And to finish things, why don't I show you that these concepts also work on other displays, even a 64x32 Hub 75 LED display. Now this display has fewer pixels, so if we ran code with text in every corner, the words would overwrite each other. But let's modify this code so that there's a single label in the middle. Then I'll show you how we can move this code to the other display. So I'm going to delete the top left and top right labels and the bottom left and bottom right labels, and let's change the print statement to read middle text. That only shows up in the console, but let's change the label text. Instead of reading middle, it should read hack! Then we'll save and run, and let's look at our ILI display. Looking good. Now let's see how it'll look on a 64x32 LED matrix. So I'm going to quit PyCharm, and I no longer need this fonts repo that I downloaded from earlier in the lesson, so I'm going to throw that away. And I'm going to create a folder on my desktop that I can use to back up everything that's currently on my Pico, so I can install that on the other Pico that's connected to my Hub 75 display. If you're only using one Pico and you're going to swap out displays, you don't have to do this step. But I'll create a new folder, call this display backup, open CircuitPy, and highlight code.py in my fonts folder and copy those over the display backup. And I'll neaten my desktop and unplug the Pico that's attached to my TFT display. And I happen to have a Pico that's already wired to a 64x32 LED matrix. If you have one of these and you need to wire yours up, I've got a whole lesson on it. Here's the wiring diagram. You can pause if you need to. And there are a lot of wires in here, but it's not too bad. You can probably get this done in 3 minutes or less. Then I'll plug my display into the power supply and plug my Pico into my computer, and the CircuitPy volume appears on my desktop. Then in the display backup, I'll copy the code.py and fonts folder onto this new Pico, replace anything if you need to, launch PyCharm, open up code.py, and we'll modify this code. I'll change the first comment to Hub 75 64x32 hack.py, and we're no longer working with the ILI 9341, so I'm going to highlight and delete this import line. And we've got the setup code for our LED matrix in our CircuitPython tip sheet, so let's open that in our browser. I'll use the find command to search for display. And if you scroll under displays, you'll see the 64x32 Hub 75 LED matrix and Raspberry Pi Pico setup. First, I'll need these import commands, so I'll highlight them, copy them, head back over to PyCharm, paste them below the existing imports, and I'm going to cut out this first line I pasted in and paste it over my first import line in my existing code. And I'll get rid of these comments and also delete the extra import bitmap font line. Next, I want to delete all the old setup code for the ILI 9341 display and replace it with the Hub 75 setup. So I'm going to highlight all the code below the DisplayIO release displays. You always want that until just above group equals DisplayIO.group. So this is all the setup code that's specific for the ILI 9341 display on the Raspberry Pi Pico. I'm going to delete this, head back to my tip sheet, and here I'll click just after DisplayIO release displays. I've already got that. Hold down my Shift key and click just before group equals DisplayIO.group. I've got that as well, so I'll copy what I've highlighted, head back to my PyCharm, and paste this code in. Now we can ignore the yellow warning. Frankly, I'm not sure why that's showing up, but our code is sound. I don't need this comment for the Matrix Portal S3. I'm not using that. And why don't we change our print statement down below to say hack Hub 75 demo. Then save your code and head into the terminal, and let's use circup to make sure that we've got all the libraries for our saved code. So we'll say circup install-a, press return, libraries installed, get into TO, and let's take a look at the display, and hey, we've got a giant hack. Notice that we've got less space around the word hack, and that's because this is only 64 dots wide versus 320 dots wide on our ILI 9341 display. Cool. And now that we know a bunch of concepts, why don't we make some changes here? So why don't we change our font to a smaller font? Why don't we make that Helv B08? Why don't we change the text to read awesome! And change our label color to red, that's 25500. Save again, and look at that. It is awesome. Fantastic work, hacker. Why don't you save this to your CircuitPython school folder, close that outermost tab, and bask in the glory of the big learning that you once again displayed. This was a longer lesson, but we covered a ton of topics, and we've got a lot more to cover with DisplayIO, so make sure that you stay tuned and continue to hack.